Okay, so I hope you will be amazed by my talk, and I will tell you about my topic, modeling and analysis in mobility software engineering. So with this, I would like to start from the very beginning, so not the complete beginning, but so I will now maybe repeat a bit. So 10 years ago, I was searching for a master's thesis topic, and I remember I was sitting in Professor Olderock's office, and he was telling me something about a lane change controller, and apparently it did not have a formal semantics yet, and he was asking, would you like to define a formal semantics for this lane change controller? And little did I knew, yes, I wanted to, and then this was so interesting that I just, as Professor Olderock already indicated, stayed and also developed the spatial logic that we have in Oldenburg and now also at KIT with me. I developed it also for urban traffic with intersections. So I think this slide was nicely summarized and better told by Professor Olderock. So I will now come to the next part. So now here at KIT, it's of course not just me. So I have my group. So also one of my PhD students is here today. I also have an external doctorand who is in Oldenburg at the DLR Institute, and also Petra Ufa, who is also here, I think, today. So it's not me, but I have also people around me working with me also on the topics I will tell today. So just to see where am I at KIT, so I'm in the Kastel Institute in the informatics faculty. So here are all my colleagues that welcomed me nicely into their ranks. And also I'm involved into the Innovation Campus Mobility. So probably you all know the Innovation Campus Mobility, but who doesn't? So it's a joint research platform between KIT and University of Stuttgart. And also there's a lot more project partners, more than 50 I read on the homepage lately. So this is really a very interesting environment for me. So as you can see on the right, it has a lot of topics. And so for me, the topic software-defined mobility, of course, is really interesting, but also the other topics are really fascinating to me. So it's nice to have such a big research environment around me. Also very important, so when I started in December 22 last year, so there was not only one junior professor from ICM, but also I started with another colleague, so it's Rania Reyes. She's also here today in the midst, so this is actually great. So we are not something like some formal team, but it feels like it's really great to exchange with you. So yeah, this is really great. So now we heard a lot about similarities of Oldenburg and Karlsruhe, so I don't want to repeat everything, but both also have yellow castles, as you can see here. So, and now actually I wanted to make some joke here about, so when I looked for pictures of castles of Oldenburg and Karlsruhe, I found a lot in Oldenburg where it was not raining, but the sun wasn't there. And in Karlsruhe, the sun seems to be always there. So I thought, okay, that's really interesting. So the weather is better here. But also in the last weeks, I was a bit critical about this. So basically, the park where I lived just went dead over the last week. So the grass was green, and now it's very light. So I really enjoy the sun here in Karlsruhe, but it's a bit too dry. So this leads me to the topic of climate change, actually. So there's one interesting thing going on right now. So there's some performance of the Badisches Staatstheater together with the KIT, actually, and also together with the ICM, which is really interesting. So last year it was the premiere, and the idea is that scientists from Karlsruhe are telling their stories about how they are working in the topic of climate change, or how their work could benefit this dangerous topic that we have here. And what I found really interesting, what I also only knew at the premiere last week, so it's actually 3 junior professors from computing science that gave some inputs into this piece. So it's not, so I was giving some inputs, but also Thomas Blesius and Pascal Friedrich, who also are both here today, I think. So this is really great, and as you can see, there are still some dates to watch this. You can find it easily if you just Google Nerds retten die Welt and Badisches Staatstheater or KIT, and I can really recommend going here because it gives some nice train of thoughts around the topic. But also with this picture of the not green grass, I would like to motivate my personal research motivation. So it's not my hypothesis, but what drives me maybe to work in the topic I am. So I'm working in intelligent mobility systems, and I like to think that if in the future we have more intelligent mobility systems, we can actually help also fight this climate change crisis. So this is what I find really great about my topic, and also about the environment at KIT, actually. So there's a lot of research going on in this direction, which I really find fascinating. So now, the story of my talk for today is that we have a professor here, and she wants to go to her inaugural lecture with an autonomous shared ride. So now the question is, okay, what does she have to do to be able to do so? Let's see. So first, she recognizes, okay, I have to model the world. So my car is driving somewhere, and I have to model this world so that the car also understands where it drives. So the idea is that we don't want to reason in the reality, because reality has a lot of variables and a lot to consider, so we could not make proofs or anything. So we take this world and we abstract from it to actually allow machine readability. So the AVs, the autonomous vehicles, could really understand traffic situations, reason about traffic situations, and we could also do formal proofs in this environment. So that's the idea. And let's look at one intersection here. So the concept that I developed is the urban multi-lane spatial logic. So it's a spatial logic where you can describe traffic situations with, and if we now zoom a bit into this, so what does this formula mean? We can see it easily here. So basically the idea is we have a chop operator, as we know them maybe from other interval logics, and the idea is that we can see here on the left we have some reservation of a car named E, and then directly in front of that there's a chop operator, and this means there's some free space, but the free space is smaller than some distance to the crossing, and then after that another chop operator saying, and then there is a crossing segment. So this is the type of formulas we can actually make with the logic. And so what can we actually do with such a spatial logic? For instance, we could, of course, have now controllers that reason about traffic situations, but also we can formalize traffic rules. So my idea is that an autonomous vehicle must also understand traffic rules if we want them to drive safely in our midst in some future. So the idea here is we formalize the rules. This means that we have to explicate implicit rules. Of course, we have also to think about rules specifically for autonomous vehicles. So for instance, there's a traffic rule stating that we should not drive with sunglasses. Probably that rule we don't need for AVs, but there might be other rules we specifically need for AVs. So this means we're not just formalizing traffic rules, but also think further, what other rules do we need that are maybe not in our Straßenverkehrsordnung as we know it from driving ourselves. We have a lot of challenges here. So if we look at the Straßenverkehrsordnung or some other traffic rule book, there's a lot of imprecise terms, there's a lot of ambiguities, and there's a lot of formal conflicts actually. So if I would just go ahead and formalize everything without thinking, we just would have conflicts everywhere. So we have to solve a lot of conflicts. And also where my work comes in quite nicely, so I have this spatial logic. So this means I can formalize all the spatial aspects of traffic. Spatial aspect meaning there's a car in front of me or there's no car in front of me, but we also have temporal aspects in traffic rules. So for instance, a rule like if you want to change a lane on a highway, you first have to look into your back mirror, then you have to set the turn signal, and only then you can actually go on the other lane. So there's some sequence of actions you have to do. So we now model the world. So the second thing we should do is we should model the behavior, of course. So we want to have an autonomous vehicle. So we should think about how could it behave. And there, just to clarify, so my work is rather on the decision layer. So I'm not talking about how do sensors do things. And also I'm not talking about how some motor works, for instance. But basically, I assume there are sensors that give me an input, and also I assume if my controller decides something, then this is actually done by motors. So if my controller says we can now enter the intersection, then this is done by the motors. So for modeling our behavior for the AVs, I use an extended version of timed automata. I don't want to go into too many details, but basically you can use this spatial logic in this controller so that the controller could perceive things like, oh, there's a crossing ahead. I now have to check some things before I can enter the intersection. We can also formalize our traffic rules with this mechanism. So this means also traffic rules have very often the structure that there's some detection part, something like if there is a pedestrian crossing ahead, you have to do something, so give way, for instance. So this means we can actually nicely also formalize a lot of the rules using such an extended timed automaton. We also formalized a protocol for turn maneuvers at intersections. So the idea here is basically if a crossing is ahead, I have to check that no potential collision with any other cars would occur, and only if I check this and everything is free, I may enter the intersection. So this is a very brief summary, of course, of the protocol itself. So to summarize, we talked about modeling. So we had some mechanism. We have this spatial logic. We have seen abstract models for traffic. We have seen that we have to formalize traffic rules. And we have these protocols for doing maneuvers like turning at intersections, or maybe also for following traffic rules. And now the second part, of course, we have to do if the professor wants to come to her lecture with an autonomous car. She has to analyze the specification. So it's nice that we can specify a lot, but it's still the question, is it good what we formalized? So let's look at this. The idea is we have this logic, we have the model, and now we want to have proofs, we want to use model checking, and we have different types of properties that we examine. The first one being safety, where now safety in this sense means I now here have some statistics of the World Health Organization. So basically 1.3 million people die each year as a result of road traffic crashes. So this is a value from last year. And I calculated before how many, I think it was 150 deaths per hour, something like this. So a lot. So it's really crazy. And also it is stated what kind of risk factors actually exist for such road traffic fatalities. And you can see by my indication here, the green ones, it's basically all human errors. So it seems quite obvious that we can actually help to have more safety in road traffic, to help this goal that the United Nations actually have of halving the road deaths by 2030. So the resolution is from 2020, and the idea was within the next 10 years we want to halve the deaths. So I think I remember I read this last year. We're not on the best way there. So after 2 or 3 years, it's not enough actually. So I now claim we can actually help towards this goal if we use intelligent autonomous vehicles. In my case, safety means it's something spatial in the sense that if a collision occurs, 2 cars are spatially in the same place, you could say. So this is why I call it a spatial property, which I can actually formalize with my logic and could also then, through the logic, actually prove that the protocol that I have actually is safe. The second property I also examined is liveness. So here now the motivation is, it's nice if we have a safe car, but basically I could have an autonomous vehicle that never moves, and then it's safe, but it also does not really do anything. So this means we want to have actually also something like liveness, meaning here, if I want to do something, my mechanism actually manages to do this thing at some point. The finer version of this is bounded liveness, meaning that we don't just finally in 50 years pass the intersection, but we actually might pass the intersection with some probability after 2 minutes or something like this. I could also formalize this, and now I examined this with UPAL and UPAL SMC, and this means that I basically formalized something like a liveness property using timed computation tree logic, and could then also show that liveness holds for a version of my controller. I also examined fairness meaning not only should I always want to reach the goal of my car, but it's better if the cars sort of cooperate, and if, in best case, all goals of all cars together are met. I don't want to go into details here, but instead I just skip to my next property, which actually is explainability. Now, explainability means there's some function maybe of our autonomous car which is a bit surprising, and we didn't think about this. So the idea is then the autonomous car should maybe explain something to us as a passenger so that we can trust the vehicle more. Or also, actually, so a lot of us here are computing scientists or engineers, so we have all sort of systems, and systems tend to get more and more complex. So they can do more and more fancy things, but they also get just more and more complex. So I actually also like the idea that with explainability, the systems could explain themselves to us experts. So sometimes we also don't understand all our systems at all time. So it's not just explainability for end users, I would claim. So now here I developed a framework with some colleagues. So here the idea is the system is observed, and if something strange happens, it is triggered that an explanation should be given. And the idea of where does this explanation actually comes from is that if we already have system models, so I already specified a crossing controller, I specified something to formalize traffic rules. If I already have all these models, I should be able to get the explanation from this model. So I don't want to have some engineer sitting there and writing down explanations manually. This is just error prone, and if the system updates, the engineer has to start writing new explanations. So we want to get these explanations directly from the models that we have and then extract them so that we can have some internal version of explanations. A very recent cooperation, actually, this is already something I'm working on with another ICM junior professor. So this is Andreas Wortmann from University of Stuttgart, as well as a colleague from RWTH Aachen, Judith Michels. And we're working on making digital twins self-explainable, where here the idea is we have different system models to explain digital twins. This means that we also get several explanation models and have to think about how can we, if we have, let's say, 10 system descriptions, how can we still get one explanation model from this? So maybe some of the system models describe the same behavior. We don't want to have everything double, so we have to refine the models in this case. So the last topic I would like to briefly cover is morality. Where here I claim, so I said before, we have a lot of conflicts between traffic rules if we just formalize them, but also in different situations, new conflicts can arise. So I just have some examples here. So for instance, in some situations, we human drivers, when we drive, we just break traffic rules to help some bigger goal. So if there's some emergency vehicle coming, you're driving onto some greenery at the side to let it pass, because this is more important at this point, although normally you are not allowed to just drive onto this greenery. So this means then we actually break traffic rules. Also, we have conflicts between traffic rules. And rules can be ambiguous, so it's not completely clear what they mean, but we humans, we sort of know what to do because we have this common sense. So now the question is, how can we bring this common sense into AVs? So this intuition, I can do this and that if something bad happens. So the question sort of here is, if I would have moral rules, maybe I could decide these things. So the idea of we let the emergency vehicle pass, this is a moral rule actually. So the greater good is to help save the person in the emergency vehicle, and breaking the other rule does not mean something that bad in this situation. So the idea is that currently we are trying to classify types of conflicts that can happen when traffic rules are used. And then of course we want to find solution strategies for all these potential conflicts that can happen. So then, something very important here, of course, we have also a lot of dilemma situations. So a lot of you heard probably about things like the moral machine. So basically where a dilemma situation would be that the question is if a car has to either evade to the left or to the right, and on the left there is 2 elderly people, and on the right there is 1 very young person, where should it go? So this is a dilemma situation, and I claim at least that I cannot solve this. So the idea is some of these conflicts have to be solved by experts, so not everything can be done and decided by the AV. This means that also here I come back to explainability. It would help the experts, let's say lawyers or ethics experts, it would help them to solve the conflict if they would have more understanding of the conflict. So here explanations for lawyers, for instance, would be interesting, where I'm also working on with a colleague currently. So with this I conclude for now. So we have seen mechanism to model traffic situations, to model behavior, and we have also seen methods to analyze actually some of the properties like safety, liveness, explainability, and also moral acting. So this is somewhat my first summary. I would also briefly like to say, so I'm also doing teaching, so currently I have a master lecture, which is called Time System. I'm also giving a pro seminar, and I will very likely give a second version of Time System next term, because some of my students asked me if I could do something like this. So what I want to say with this, I'm also actually bringing my research into my teaching, which I really like to do. I really enjoy the research environment I found here in Karlsruhe. So these are just some institutions, some groups that I already have talked to, where I already found a lot of very interesting topics to work on together. So it is really great. So I had great discussions with colleagues from these institutes. I probably forgot some. So if somebody's saying, hey, we also had a very nice discussion, why is my institute not here? I probably forgot this. So, but this was not with a bad meaning or something. Please just tell me. And also, if we did not yet talk, please, if you found my topics interesting, just come up to me and we can discuss. So I'm really happy to do cooperations. So I have a lot of thanks. So of course, I would like to thank the other speakers today. So 2 we already heard, 1 we will hear later. Of course, Andre we will also still hear. Here's a lot of names. I will not say them all. So I really want also, of course, to thank you, audience, for being here. If you weren't here, it would be a bit strange of me to talk to an empty room. So it's great to seeing all of you here, that all of you followed our invitation. Yeah, so really thank you also for the nice discussion. Thanks my group for always helping me out. So this is really great. Of course, also thanks Professor Olderock for supervising me during my PhD time. Also thanks to Martin Frenzle, who could not come today, who also mentored me throughout my postdoc phase, and also, of course, sort of helped me to now be here at KIT in front of you. Last but not least, very important, she's not in the room right now, so Lawrence Böhnke is currently organizing everything, organized also before everything. So without Lawrence Böhnke, we also wouldn't be here. So she's really organizing everything. So whatever you will drink and eat in less than an hour. So she organized that all these things are here. So say thanks to her. And yeah, so now this is my last conclusion. So unfortunately, of course, I still have a lot of research ahead of me. So this means I was not able to create the autonomous vehicle to bring me here. But I think I'm on a good way, also with all the help of you colleagues here and the other colleagues that are not here today. So I'm really happy to be here. It's really great. And yeah, so with that, I would like to say thank you for listening.